Okay, any questions? No questions? So for the second midterm, I think some of you got confused. So every team will select only one paper. Your presentation as a team will be on one paper and you will all be preparing reports on that same paper, okay? So now that's a part of the process. You might like one paper, your teammates might like another paper, it will happen. So try to make a case, try to convince everyone why they should go for your paper, okay? And then no class on Friday, so please use the time to go through the papers and decide what to do. That's the most important step for you to do, is to decide which paper to work on. No questions otherwise? Okay, so last time we talked about, last time we did a single phase, two component system, right? We did a single phase, two component system, but even in this, we showed how single phase could split into two. We got hints of this when we saw that the free energy delta G of mixing, delta mixing of G versus composition, XA is equal to 1, XB is equal to 1, showed some strange behaviors, some things like this. That is when it splits into two phases of two different compositions. But we really didn't talk about it. Most of the time, it was just a single phase, things mix uniformly all the time, and everything is wonderful. So now, today, we will talk about, again, two components. So let's say XA and XB are their mole fractions, but also two phases. Now, it's very well possible that every phase on its own shows some complicated behavior. Right now, it's just simple. These two phases that we are going to consider are going to be liquid and vapor. And we will try to understand how does a phase diagram for this look like. And in this, we will come back and revisit this problem after we have done this to get a sense into what really happens when you have a bump in the free energy like that. We will get back to it, okay? So in order to do this, let's start very, very basic. So we are talking about constant pressure, let's say atmospheric pressure. So my question for you is, at constant pressure and at a given temperature, which state function should we look at in order to decide which phase will be more stable? Gibbs or Helmholtz? Huh? Yeah, so Gibbs, right? Is everyone confident with that? When would you do Helmholtz? Temperature and volume, right? So we are talking about temperature and pressure. We have kept the pressure and we kept the pressure constant. We are talking which temperature will liquid change to vapor. Okay, so constant pressure, our free energy of interest is Gibbs free energy. Okay, so if GL is less than GV, this means liquid has lower free energy than vapor. So by L, I mean liquid, by V, I mean vapor. And this would mean liquid is more stable. And if we found at a certain temperature that GV was smaller than GL, it would mean vapor is more stable. So good. My next question for you is, at high temperature, which one should, at very, very high temperature, which phase should be stable? Liquid or vapor? Someone from this side. What do you think? Hello, what's your name? Nicole, what do you think? At high temperature, should you have vapor or liquid? Vapor. Don't be doubtful, right? When you heat something up, it becomes steam, right? It won't become solid. So Nicole thinks that at high temperature, vapor should be the stable phase, right? This is our common sense, and this is mostly correct. When you heat everything becomes ideal gas at very, very high temperature. So this means that the vapor free energy, the vapor Gibbs free energy should be lower than the liquid free energy. Can we justify this? Should this really be go ahead. How about enthalpy? Yeah, so let's go systematically, okay? You're going in a slightly this type manner, right? Let's not do that. Let's think systematically. We are talking about G. What is G? G is equal to H minus Ts. As you increase the temperature very high, at low temperature, this would be approximately H, right? At T close to 0, correct? Because entropy does not matter. The term proportional to entropy goes to 0. But at very high temperature, this will approximately become close to minus Ts, because the enthalpy itself does not depend on temperature. The entropy itself might or might not depend on temperature. That's another story. But the term that you're multiplying the entropy with, that increases more and more, right? So at very high temperature, Gibbs free energy is almost approximately minus T multiplied by entropy. Now, which one has higher entropy, vapor or liquid? Huh? Why? It just vapor moves around a lot, right? If you think about the K log W formula, vapor has higher entropy. So the entropy of vapor is much more than entropy of liquid. We use this argument, these type of things. Remember, we didn't use this one. We looked at volume of vapor much more than volume of liquid when we did the Clausius equation, right? So this means that now we are multiplying it with a minus T sign, right? So once you multiply with a minus sign, it means that Gibbs free energy of vapor is going to be much smaller than the Gibbs free energy of liquid. Okay, I'm going to pause here just for a moment for people who came late so they can catch up. So we are talking about two components, liquid, and two components, A and B, and two possible phases, liquid and vapor. And we just showed that at very high temperature, vapor should exist, as common sense suggests, and also because Gibbs free energy is lower, because Gibbs free energy is almost entirely entropy at very high temperature. So let's keep this in mind, and then let's start decreasing the temperature, and then let's see what happens. We are not going to make it so low that the solid starts to emerge. At very low, at 0 Kelvin, everything will become solid, right? There's perfect crystal. That is just a crystal. We are not going that low. We are staying in a high enough temperature. So I'm going to move my page now. So we just showed that at T is equal to T1, which is some very high temperature, G of vapor is smaller than G of liquid. Therefore, vapor is more stable. Now let's decrease the temperature. Let's go to some T is equal to T2, which is smaller than T1. Okay. And I'm going to draw a box in this corner where I'm going to construct my final phase diagram, and I will start filling this gradually. So in this box, the x-axis is amount of xb. So this is xb is equal to 0, and this is xb is equal to 1. It's a binary system, so anytime you know xb, you know xa also. And this over here is T is equal to T1. We have T2, and we will have other temperatures as we go further. So at very high temperature, we expect that for any concentration, we are going to have only vapor, right? Doesn't matter what concentration you have, you are only going to have vapor phase existing. Now let's decrease the temperature. And so let's draw this also. So this is the phase diagram, but in parallel, I'm going to draw one more thing, which is, again, same idea. This is xb going from 0 to 1. And I want to draw the free energies of both systems. So I just showed that the liquid has higher free energy than vapor at T is equal to T1, right? So the liquid free energy will look something like this, and the vapor free energy will look something like this, okay? So this is G liquid, G vapor. Everyone happy with this? Anyone unhappy with this? Okay, so all we have said is that at any composition, vapor will have a lower free energy. You can do whatever you want, you're just gonna get vapor, which is common sense, right? at very, very high temperature. Now we decrease the free energy. And my question for you is, so we again have 0, xb, going from 0 to 1, t is equal to t2. My question for you is, what will happen to the two curves? Will they move up? Will they move down? Which one will move more? How do we answer this question? And remember, this is at the same pressure. We haven't changed the pressure. All we have done is change the temperature. Go ahead. So you're saying vapor will move? So Andrew is saying vapor will move more than the liquid, but what you did not tell me, Andrew, is are both going to move up or down? Why will they move up? You're absolutely correct. So what Andrew is saying here is to ask us to look at the fundamental relation, which is dg is equal to vdp minus sdt, right? So you're correct in thinking of g is equal to h minus ts, but this is even better. And we are thinking about pressure, right? So this allows us to talk about change in entropy with change in temperature at constant pressure. That's what we are interested in, right? And that is minus s. Can entropy ever be negative? No, right? Third law of thermodynamics says that at zero Kelvin, entropy can be 0. And as you increase the temperature, entropy increases, right? What does this mean? This means that partial G by partial T at constant P is negative. Furthermore, we know that entropy of vapor is more than the entropy of liquid. So first of all, what does this tell us? This tells us what is the meaning, what is the physical meaning of this partial derivative? This partial derivative means that if you change the temperature by a certain amount delta T, the change in delta G for small enough change in temperature is going to be given by delta T multiplied by minus S, right? That is the meaning of the partial derivative at constant pressure. So if I decrease the temperature, then what is the sign of delta T? I decrease the temperature. So delta T is negative, correct? T2 is smaller than T1. So this is negative. Minus S is also negative because entropy is always positive. Therefore, delta G is positive. At the same, so that explains that both of the curves will move up. So this G liquid will look something like this. It moved up just a tiny bit. But the question is, which one will move up more? Can we explain that on the basis of this equation? We can, right? For the same delta T, the magnitude of minus S is more than for the vapor, than for the liquid. Therefore, the vapor curve will move up more. So delta G vapor is going to be more than delta G liquid, okay? So the black one will move up, but the blue one will move up quite a lot. And it might start to look something like this, like it's almost caught up. It might not, depends on the precise value of T2, but it's a race going on. It might or might not catch up, but it's gotten quite close. Let's decrease the temperature further, okay? Let's decrease the temperature even more. Now we are talking about T is equal to T3. Same behavior, both of them will move up, but black one, the liquid, will move a little bit up, while the vapor one will just go boom. It will move up a lot because the rate at which it moves is proportional to the entropy. And in liquid, vapor has a lot of entropy. So now what will happen is the black one also maybe moved a little bit, but the blue will now cross it. And it will start to look something like this. And of course, it has to go and meet the axis over here. So now there is a crossover point. So if we go back to our phase diagram, at temperature T2, at all compositions, blue is below black, right? I should, in this picture, call this as, yeah, vapor is, oh, I'm using blue. Okay, good. So this is all vapor. And at temperature T2, you can see blue is still below black, right? So at temperature T2, it's still going to be all vapor. But something interesting happened at T3. At T3, if you are until this composition, which one has lower free energy, liquid or vapor? Louder, please. Liquid. And what happens at that crossover? Vapor becomes. So you can see a phase transition is happening, right? As we change the composition. So at this composition, you will start to see, and this is where, so if you just looked at, let me zoom in a little bit. If you just looked at this one, this picture would tell you that right until this composition, it should be all liquid. And right after this composition, it would be all vapor, right? Because that's where the free energy changes. In practice, that is not true. In practice, something more complicated happens. You have a middle region in which, and we are going to get to that in a moment. So this, sorry, this is wrong. In practice, you have L plus V, and V. And we will explain that just in a moment. But for now, you can see, only thing you can definitely see on the basis of this is that the free energy curves intersect. And at some point, instead of having just liquid, you change into vapor. And my claim to you right now, without proof, is that it will be a bit gradual. It won't be all liquid suddenly changing to all vapor. You will have liquid, some vapor will start to emerge. You will have liquid and vapor coexisting, and then you will have all vapor. So in the phase diagram, this thing is going to look like the first, so to the left of this, we are going to have some liquid. Then we will have a small region where we have liquid plus vapor, and then again, all vapor. Okay. Now let's make the temperature even lower. Let's go to T is equal to T4. So this is all quite applied, and really we are using only one equation in making all of this. That partial G by partial T at constant P is equal to minus S. Okay, that's the only equation we are using. And what we are doing here is to T is equal to T3 less than T2, T4 less than T3, T5 less than T4. We are just decreasing the temperatures and going down more and more. Okay, at this one, what will happen? Liquid will again move up. Vapor will move up even more. And let me draw the final one, which is T is equal to T5. Let's actually first draw T is equal to T5, which is a very, very low temperature. So at very, very low temperature, let's say close, so low that you're not going to get a solid to form, but it's low enough. At extremely low temperatures, what do you expect the liquid and vapor curves to look like compared to the first one? Your hint is T is equal to, yeah, go ahead. It completely flips, right? The liquid will be lower all through, and the vapor will be higher all through. So at a very high temperature, the liquid has continued to move up, but it hasn't really caught up because the vapor has moved up so much that it completely flips. So at any so 0 xb1, and in this case, G liquid is always lower than G vapor, which makes sense, right? If you cool a vapor a lot, it will become purely liquid. So at very, very low temperatures, what we are going to get is only liquid all through. So this is T5. Now let's try to think about T4. So T4 is an intermediate temperature in which they are both still intersecting. The question though now is, what should happen to this intersection point? Should it move to the left or to the right? This needs a bit of geometric imagination. Why? You already answered. Someone else? It kind of makes sense, but you have to think a bit hard about it, right? So it's two curves are moving up and it just keeps, yeah. You could construct some peculiar cases where it doesn't. You can actually mathematically prove that it will move right, but if you think about it, it's not too complicated. And if it confuses you, you know how to find and Marco on Slack. So it will look, let's see if I can draw this. It's going to look, so the liquid looks something like this, and I have to draw a really big figure to get both sides. And then this one is going to look something like this. Okay, so the intersection point has moved to the right as relative to this one. So here you had the intersection point over here, and here the intersection point is further to the right. So what this means in the phase diagram is you will have some, and so at T4, you will have some liquid, you will have some more liquid, and then you will have liquid plus vapor, and then back to liquid. So let me redraw. So you're starting to get hopefully you're starting to get a picture here that a two-phase region is emerging in this thing. If you join this boundary over here, you can see that a two-phase region is starting to emerge. Okay, and I have not yet proved to you as to why it should be liquid plus vapor. Why should it not be just a straight line where the liquid changes to vapor? We will talk about that just in a moment, but let me redraw this in a bigger picture on the next page once everyone has caught up. Any questions about this? Go ahead.
Is there any reason the plus are symmetric?
No, I'm just drawing it there. A is different to B. They can be, but it's more complicated. Most of the times A is not B. You're thinking of copper, zinc, or any two chemicals, they are not symmetric. Let's go to the back. Yeah. Did I switch the colors? You're right. Good spot. Very good spot. Because if that did not happen, then the extreme right of the phase diagram would be all this. So you're correct. What's your name? Noah. Noah is absolutely correct. So what Noah said here is that, let me just draw the blue one first. Happy now, Noah? Good. Okay, wonderful. So let's draw this picture, this square over here on the next page, how it looks like. And it could be symmetric, and it could get very complicated. This is like the simplest phase diagram, but this basic principle applies to all phase diagrams. And materials tend to have, or chemicals tend to have, very complicated phase diagrams. If you go and look up the iron carbon phase diagram, it's full of complicated features, and they basically decide how you make steel, or what composition do you have to add. The iron carbon phase diagram is so complicated that once you add like parts per million of something like vanadium, the phase changes, and it's super complicated. And you have to know the complicated phase diagram in order to know this. But people have known the iron carbon phase diagram with different alloying elements for close to 1,000 years, even before there were any atoms or things like that. They just had an intuitive sense for it. So when I was doing my undergrad, I went to a steel plant, metal and steel plant, and there was a guy there who was completely illiterate, and he could just tell which phase is forming by looking at the color of the flame. It was crazy. He was like, oh yeah, this is around 0.1% carbon. You just look at color of flame and tell us. That's just like 40 years, 50 years of experience. Okay, so this picture that I drew on the last page is eventually going to look something like this. So we have temperature on this side, and we have composition XB on this side, and you will get a curve like this. It could be symmetric, depends on the elements. if A and B are same, then there is nothing really going on, right? It's just one component, one phase. There is no phase. You go back to something like water phase diagram, But it can be symmetric, it can be asymmetric, but this is the general framework. Vapor is at the high temperature. In the middle, you have liquid plus vapor, and in the bottom, you have liquid. Okay, go ahead, Ryan. So let's think about it. The Gibbs phase rule is F is equal to C minus P plus 2. How many components do we have? C is equal to 2. And which phase region are you talking about? Oh. So he's saying that in this region and this region, if you think about it, both are two-phase regions, but they seem to have 2 degrees of freedom, right? How does it happen? The reason it happens is because of pressure. So you have to pressure is the other coordinate we are not considering, but think about it. It's a good question. So this accounts for pressure over. So yeah, you can. That's why some books don't talk about it as C minus P plus 2. They talk about it C minus P plus 1. Okay, so the most important thing now is to understand this T is equal to T3 behavior and see what's going on. Why is it that we formed liquid plus vapor? Why is it that liquid did not change to vapor on its own? Okay, so in order to do that, I'm just going to go to the next page and draw a big picture because it will take some time to do that. So at T is equal to T3 or T is equal to T4, we had a picture that looked like this was X is equal this was X is equal to XB going from 0 to 1. And we had, what did we have? Let's look at T3. We had a liquid curve that was in black, and we had a blue curve, which was vapor. And let's draw both of them. So we had liquid curve, which was something like this. And we had a vapor curve, which was something like this. Okay. So this is liquid and this is vapor. So it's clear that if I go till this point, to the left of this point, to the left, GL is lower than GV, right? And to the right, GV is lower than GL. So if you think about this one, it appears as if there is no reason for liquid plus vapor to coexist. You should just have liquid and then all of it should change into vapor. However, it turns out that liquid and vapor coexist. Let's try to understand that why. And what we are trying to understand now is known as Maxwell's common tangent construction. Okay. So in order to do this, let's see if I can draw a better curve to make my life easier. So what I'm going to do here, it applies to that one also, so you don't have to really read all, but I want something which is a bit like this, so I can do a bit easier. Okay. So the special points here are, anyone remembers what's a tangent to a curve? Slope, but what exactly is a tangent? What's special about a tangent? Go ahead. It touches a curve only at one point, right? A tangent is something that touches it and takes off, right? So to this black curve, you can draw tangents at many points, right? So this is an example of a tangent, right? It touches it at one point. If the curve is complicated, it go and touch it somewhere elsewhere also, but locally it touches it at only one point, right? So that's just your geometry refresher. You can draw lots and lots of tangent. Over here, you will have some other tangent. there is one special tangent in this picture. It's called a common tangent. There is one and only one line which can serve as a tangent to both curves. And that's going to look something like this. Why is there only one tangent? I could draw it over here. Let's say I have two curves like this. I could draw various tangents to this, right? If I draw a tangent over here, it will not be a tangent to this curve on the left, right? If I draw a tangent over here, it will not be a tangent to this curve on the left. There is only one special tangent which can serve as a tangent to both of them. And once you know what is that curve, you can figure out what is the point at which it is a tangent to both of them. So let's call this one as, what should we call it? Let's call it as x1, and let's call this one as x2, okay? So this curve in green is the common tangent to both phases. We had our G liquid and we had our G vapor, and it's a common tangent to both of those. So tangent means mathematically what, so once we, the tangent is a straight line here, right? You could come up with tangents which are not straight line. That's another story. We're talking about straight lines. So if this is a straight line, and if I ask you to calculate the slope of this straight line, how would you do that? What is the slope of the common tangent? I want you to calculate it in two different ways. How do we do that? Any ideas? Yeah. Let's just take the derivative. So tangent slope means derivative, right? So Ryan said, let's take the derivative. Anyone else wants to help me? Derivative of what with respect to what? Noah, what do you think? Difference derivative of GL with respect to XB at point X1. This is the slope over here, right? And what is the slope over here at this black point? Noah? And these should be equal, right? Because the slope is the same. But have we previously seen the derivative of G with respect to X? Does it have a name? Huh? It is the chemical potential. It's our hero. It's the chemical potential. So what we have just shown is that mu of liquid at X1 is equal to mu of vapor at X2. And what does chemical potential being equal mean? That means equilibrium, right? The liquid is in equilibrium with the vapor. And now you can show, and this is the really interesting part, and let me zoom in just a bit. If you had a point over here where you thought that the liquid has lower free energy than vapor, it's better for this point to drop down. So what I mean is that if you had a free energy G2 at this point, G2 would be higher than, so G2 is all liquid. G2 is all liquid. And this would have smaller free energy, higher free energy than having certain amount of liquid with composition X1 and certain amount of vapor with composition X2. Okay, so G2 all liquid, and let's call this one as G1, which is mixture of liquid plus vapor. So you can see from the curve that I have 2 points, right? G2 lies on the black point, on the black curve, and G1 is on the common tangent. Clearly, the common tangent is lower, right? The way we have drawn it, it's always going to be lower than the black curve. This is really not math, it's just purely intuition. So let's try to understand it slowly. Everyone agrees that the green curve lies below the black point, right? But now the question is, what is the value of this green curve? So this green curve, this point over here, let me give it a color for, whoa, moved. Crazy. This one is a combination of liquid with composition X1, liquid with composition X1, and vapor with composition X2. And they can coexist. These are two very special values of liquid and vapor compositions at which they can coexist. Why can they coexist? Because their chemical potentials are same. You could not just split it into two other compositions and expect them to coexist. Your chemical potentials would be different and they would not like each other. But if you drop down from here to this point, they can split into these two compositions. And we know that since the slope is the same, their chemical potentials are the same. Therefore, they can coexist. And we know that it is lower than the black point, therefore the free energy is lower. So in this region, we have liquid. In the middle, we split into liquid plus vapor. And over here, we split into vapor. So this is super, super important. And it shows up in all complicated phase diagrams. Maxwell, of Maxwell's electromagnetism, was the first person who really thought of this. So this goes back to him. And the most interesting thing in this curve is, I drew the black point over here, right? Now let's say I move my black point and make it the red point over here. Now what should it do? Should it be all liquid or should it become liquid plus vapor? It should again become liquid plus vapor and drop down to this point. Now when it forms liquid and vapor, what will be the composition of the liquid? It will once again be X1. That's not going to change. The only thing that will change is you will have different, more liquid or less liquid, but the composition of the liquid will be the same. Okay, so these are, I know I see some slightly blank faces in spite of the masks because this is a lot, but go and think about this. Read this in Atkins. Atkins talk about it. And if you go and Google for Maxwell's common tangent construction, you will find a lot of material. The key picture here is the two curves, the liquid and vapor, intersect. Once they intersect, anytime two curves intersect, you can construct a common tangent. One straight line, which has the same slope for liquid at this point as it has the slope for vapor at this point over here, which means that liquid with this composition X1 can exist with vapor at this composition X2. You get very unique values for X1 and X2, okay? And that means that if you are at this composition over here, instead of being purely liquid, you definitely don't want to become all vapor because vapor curve is higher, but you can split into a combination of liquid and vapor given by these combinations. Are there questions in the back? I see some. You have a question? No? Everything clear? Okay, if you have a question, please ask. And the interesting thing is, even over here, it will drop down to this common tangent. So let me draw this figure once again, because I have already cluttered it quite a lot. Well, so I have some curve and I have some other curve, okay? And I draw my common tangent. That looks oh, that was bad. That looks something like this, okay? So this is liquid and this is vapor. So at any point here, you are better off splitting into liquid with composition X1, liquid with composition X1. So liquid will have X1 moles of the B because this is measuring B, and the vapor will have X2 moles of B. So at any point you are splitting into, and this is super interesting. So anytime you are forming new vapor, it's always going to have the same composition. The only thing that will change is the amount of vapor you form. So here's a question to make sure that you're understanding. As I'm moving in this direction, am I going to form more vapor or less vapor? More vapor makes sense, right? Because at this point, well, there is no change. You have only 100% vapor. But the super interesting thing is, due to Maxwell's construction, which really follows from the wonderful properties of the chemical potential, you are going to form liquid and vapor of the same not of the same composition, but the fixed composition. Irrespective of where you are, you will always have liquid and vapor of the of a constant composition. Go ahead.
So you will never have a liquid that has a higher composition of than like X or further to the right X1, and you'll never.
In this picture, no. So anytime, yeah, I will come back to you, JP. So you will always form liquid with the same composition X1, volume with this vapor with the same composition X2. And of course, the curves could be changed, but this basic picture applies. And next time we are going to study about something called Lever rule, which will allow us to calculate how much of liquid and how much of vapor. Yeah, JP.
Should there be a delta G curve where previously you said there could be multiple maxima and minima for the delta G curve, so it could go through multiple transitions?
Oh yeah, it gets crazy. It gets really wacky. It gets super wacky. Especially those of you who are in material science will see a lot of these curves sooner or later. It gets very complicated. You will have one curve with 3 bumps and the other curve with 4 bumps. And then actually, when I was an undergrad, it was a lot of fun to write codes in Wolfram, in Mathematica, to calculate, or in Maple, how to calculate the common tangent for this. It becomes non-trivial because you have many possible common tangents, and you have to figure out which one will fall. And you will have not just we are doing just simple phase diagram, and as you can hopefully appreciate, we can spend a lot of time on phase diagrams, right? But this is the key machinery. You have to think about and the why common tangent, because tangent is slope and slope is chemical potential, and common tangent means same chemical potential, right? So someone asked me on Slack yesterday, I think it was Marco, like, what is the meaning of the sign of chemical potential, right? So sign of chemical potential does not really mean much. What matters is the difference of chemical potential, right? So anytime you have an electric potential or a chemical potential or any type of potential, potential is a gradient. It tells you which direction to move in, right? So if I have $10 and Nicole, right? And Nicole has $12. Nicole is still $2 richer than me, right? So I would like to take $2 from her by any means possible. But now if I have $6 and Nicole has $8, she is still $2 richer than me. I would still like to take $2 off her. So the difference is what matters. You could go to a limit where Nicole has -$5 and I have -$7. I mean, she is still less poor than me. In other words, she is richer than me, right? So the sign does not matter, except when chemical potential is always 0. And that's a funny setup where you have things such as phonons and photons, where the chemical potential is always 0. So you can create as many photons as you wish. No one has seen a photon. It's fake. I mean, no one has really seen an electron, if you think about it. Have you seen an electron? I haven't. We talk about it as if it's so obvious, but I don't know what's an electron. It's a quantization. It's funky. So this is Maxwell's common tangent construction. And this is a lot of information. What I want to do is to tell you what we are going to do next time. Please read up on Maxwell's common tangent. And next time, we are going to talk about something called lever rule. Lever rule means we will go to our phase diagram. Now we know it exists like this. Let's say this is vapor, and this is liquid, and this is liquid plus vapor. And this is composition of XB, and this is temperature. At this point, we will have vapor. So the reason why this is such a line is called a tie line, a horizontal line. And this line is very interesting because at any such point, you know what is the composition of the liquid. The composition of the liquid will be given by this point over here, and the composition of the vapor will be given by this point over here. But Lever rule will allow us to calculate how much liquid and how much vapor are you going to form. We know over here it's all liquid. We know over here it's all vapor, but it will allow us to answer what happens at a given point in the middle. So read up on it. We will do Lever rule. And then, so we have no class on 19th. Then what is next week? 24. We have class on 22nd, right? Monday. 24, we have no class. Then we have class on 29. Then on 1st December, you are all making your great presentations that you are going to send me before that. First will be presentation. And then we have basically around 9th December or so, we have 3 or 4 classes left after Thanksgiving. What we are going to do is to study about equilibrium constant, 2 classes, and then I will take 2 classes to talk about kinetics. Because thermodynamics, there is one deeply unsatisfying thing about thermodynamics, is it does not tell us when will something happen, right? It tells us, yeah, it's spontaneous, it will happen. But it might take age of the universe, and we'll do a little bit of kinetics. And I will have 1 or 2 classes where I will review the whole semester. And there is going to be 1 homework after Thanksgiving.